Welcome, everyone. Today, we're stepping into CCSP Domain 1, and this is really where the cloud security mindset begins. Now, when people first hear cloud concepts, architecture, and design, it can sound a little abstract. But here's the good news. This domain is not about memorizing random cloud terms. It's about understanding how cloud environments work, who is responsible for what, where the risk lives, and how security changes when we no longer own the physical infrastructure. Think about traditional IT for a moment. If you owned the data center, you could point to the servers, the cables, the racks, and the physical doors. In cloud, that changes. You may still own the data, the business risk, and the compliance obligation, but someone else owns the building, the hardware, and many of the underlying services. So the big question for this session is simple. How do we secure something we don't fully control? That's the mindset we're going to build today. We'll cover the core characteristics of cloud, service models, deployment models, cloud roles, shared responsibility, virtualization risks, data protection, logical controls, DevSecOps, compliance, emerging technologies, and resiliency. By the end, I want you to think of it less like someone memorizing terms and more like a cloud security architect making risk-based decisions. Let's start with the foundation. Before we call something cloud, it has to behave like cloud. That's where the 5 essential characteristics come in. The first one is on-demand self-service. This means users can provision resources when they need them without waiting for a person to manually set everything up. Think about spinning up a virtual machine, storage bucket, or database in a few clicks. That speed is powerful, but it also means governance has to keep up. If anyone can create resources quickly, what happens if they create them insecurely? The second characteristic is broad network access. Cloud services are available over standard networks and can be accessed by many types of devices. Laptops, phones, tablets, API, and automated systems can all connect. That flexibility is why cloud is so useful, but it also expands the access surface. The third is resource pooling. This is where the provider uses shared infrastructure to serve multiple customers. That's called multi-tenancy. You may not know exactly which physical server your workload is running on, and that's normal in cloud. The provider abstracts that away. The fourth is rapid elasticity. Cloud can scale out and scale back quickly. Imagine an online store during a big sale. Traffic spikes, more compute resources come online, and when the rush ends, those resources scale down. It can feel almost unlimited from the customer's point of view. The fifth is measured service. Cloud usage is monitored, controlled, and billed based on consumption. You use more, you pay more. You use less, you pay less. It's like a utility bill for computing. Here's the exam angle. If one of these 5 characteristics is missing, it's not considered a true cloud model for CCSP purposes. So as you study, ask yourself, does this environment provide self-service, network access, pooling, elasticity, and measured usage? If yes, you're thinking cloud. Now that we know what cloud is, let's talk about how cloud services are packaged. This slide gives us the 3 official cloud service models: IaaS, PaaS, and SaaS. Let's make this easy. IaaS means infrastructure as a service. The provider gives you virtualized infrastructure such as compute, storage, and networking. You manage the operating system, applications, and data. A simple example is launching a virtual server in AWS, Azure, or Google Cloud. You don't own the physical server, but you still manage a lot above it. From a security perspective, IaaS means you're responsible for things like operating system patching, host configuration, virtual firewalls, identity access, and application security. Next is PaaS, platform as a service. Here, the provider gives you a runtime environment. You bring the application and data, while the provider handles more of the underlying platform. Think of a managed application platform, where developers deploy code without managing the operating system directly. The security focus shifts. You care deeply about secure coding, identity and access management, API security, and OWASP top 10 risks. Why? Because the application becomes the main area you control. Then we have SaaS, software as a service. This is a fully managed application. Think Microsoft 365, Salesforce, ServiceNow, or Google Workspace. You're not managing servers or platforms. You're mostly managing users, permissions, configuration, data, and integrations. Here's a good way to remember it. With IaaS, you manage more. With SaaS, the provider manages more. But notice something important. You never hand over full responsibility for your data. The exam tip matters here. For CCSP, the official service models are IaaS, PaaS, and SaaS. You may hear other terms like identity as a service, but for the exam, these three are the core models. Now that we understand service models, let's look at deployment models. Cloud deployment models answer a different question. Not what service are we consuming, but who owns it, who uses it, and how is it shared. First, private cloud. This is dedicated to one organization. It can be on premises or hosted by a provider, but the key idea is exclusive use. The organization gets more control and privacy, but usually at a higher cost. Second, public cloud. This is available to the general public and runs on the provider's premises. It gives high scalability and flexibility, but it also introduces multi-tenant risk because many customers share the provider's infrastructure. Third, community cloud. This is shared by organizations with common concerns, such as regulatory requirements, mission needs, or industry-specific compliance. Think of healthcare organizations sharing a cloud model designed around healthcare compliance needs. Fourth, hybrid cloud. This combines two or more distinct cloud infrastructures that remain separate but are connected by standardized technology. For example, an organization might keep sensitive workloads in a private cloud while bursting into public cloud for extra capacity. The key exam point is that hybrid cloud is not just, we use two clouds. The clouds remain distinct entities, but they are connected in a coordinated way. Also, don't confuse hybrid cloud with multi-cloud. Multi-cloud means using two or more public cloud providers at the same time, such as AWS and Azure. Hybrid cloud is about connecting different types of cloud environments. So far, we've covered what cloud is, what service model we use, and how it's deployed. Cloud security is not just about technology, it's also about roles, responsibilities, and relationships. The first actor is the cloud consumer. That's the organization or person using the cloud service. In most business settings, that's us, the customer. The second is the cloud provider. This is the company making the service available. AWS, Azure, Google Cloud, and SaaS vendors are common examples. The third is the cloud carrier. This is the intermediary that provides connectivity, such as a telecommunications provider or network service provider. In simple terms, they help move traffic between you and the cloud. The fourth is the cloud auditor. This is an independent assessor that evaluates controls, compliance, and security posture. Auditors help validate whether the provider or environment meets certain expectations. Then we have the cloud broker. The broker sits in the middle and can add value in a few ways. Intermediation means the broker enhances a service, maybe by adding identity management or monitoring. Aggregation means the broker combines multiple services into one view or dashboard. Arbitrage means the broker dynamically selects the best provider based on cost, performance, or another factor. Why does this matter? Because in cloud, risk can move across relationships. You may rely on a provider, a carrier, a broker, and an auditor. If one link is weak, your overall risk changes. That brings us to one of the most important concepts in cloud security: shared responsibility. This slide is one of the most important in the entire domain. Shared responsibility means the cloud provider and the cloud customer both have security responsibilities, but the split changes depending on the service model. In SaaS, the provider handles most of the stack. The provider manages the application, operating system, hypervisor, hardware, facilities, and underlying network. The customer mainly manages data, users, access, configuration, and governance. In PaaS, the provider manages the underlying infrastructure and platform, but the customer is usually responsible for the application and data. In IaaS, the customer manages even more. You manage the operating system, applications, identity, data, and many security controls. The provider still manages the physical hardware, facilities, underlying network, and hypervisor. Here's the important part. Information, data, and governance are always the customer's responsibility. That means if sensitive data is exposed because permissions were misconfigured, the organization cannot simply say, well, it was in the cloud. The provider may host the service, but the customer owns the risk tied to its data. Think of renting an apartment. The building owner maintains the structure, plumbing, and shared areas. But if you leave your front door open, that's still your responsibility. Cloud works the same way. The provider secures the cloud, The customer secures what they put in the cloud. Now let's go deeper into the technology layer that makes much of cloud possible, the hypervisor showdown. Virtualization allows one physical machine to run multiple virtual machines. The hypervisor is the software layer that makes this possible. There are two main types. Type 1 hypervisors are called bare metal because they run directly on the physical hardware. There is no general-purpose host operating system sitting underneath them. This makes them more efficient and generally more secure. Type 2 hypervisors are hosted. They run on top of an existing operating system. For example, you might run virtualization software on your laptop. That can be useful for labs and testing, but it adds more attack surface because now the host operating system becomes part of the risk picture. So, which is better from a security perspective? For CCSP, Type 1 is considered more secure and efficient than Type 2. Why? Fewer layers, less overhead, smaller attack surface. Imagine building a house directly on a concrete foundation versus building it on top of another house. The second option has more complexity, more dependencies, and more ways something can go wrong. Now that we understand hypervisors, let's look at how attackers might target virtualization. Virtualization gives us flexibility, but it also introduces unique risks. The first risk is VM escape. This is when an attacker breaks out of a virtual machine and reaches the hypervisor or another VM. It's rare, but it's serious because it can compromise the isolation that cloud depends on. The second risk is resource contention. If one VM consumes too many resources, it may impact neighboring VMs. Think CPU, memory, storage, or network bandwidth. In a shared environment, one noisy neighbor can affect others. The third risk is VM sprawl. This happens when virtual machines are created and forgotten. They may sit unmanaged, unpatched, unmonitored, and undocumented. And what do attackers love? Forgotten systems. So how do we defend against these risks? We use strong logical isolation. We apply strict role-based access control to the management plane. We patch rigorously. We monitor resources. We maintain accurate inventories. And we avoid giving broad administrative access unless it's truly needed. Here's the practical takeaway. In cloud, the management plane is extremely powerful. If an attacker controls the management plane, they may not need to exploit the workload. They can simply change the environment. That leads naturally into data protection, because at the end of the day, cloud security is really about protecting data. Data exists in three major states: at rest, in transit, and in use. Data at rest means data stored somewhere. That could be in a database, object storage bucket, file system, backup, or disk volume. The threats include unauthorized physical or logical access. The controls include encryption, key management, and sometimes data dispersion. Data in transit means data moving across a network. For example, a user connecting to a web application or an application calling an API. The threats include eavesdropping and man-in-the-middle attacks. The controls include TLS, IPsec, VPNs, and dedicated private connections. Data in use means data actively being processed in memory. This is often the hardest state to protect because data may need to be decrypted to be useful. Threats include memory scraping and insider threats. Controls include confidential computing, trusted execution environments, secure enclaves, and in advanced cases, homomorphic encryption. Here's a simple way to remember it. Stored, moving, processing. Stored data needs encryption at rest. Moving data needs encryption in transit. Processing data needs stronger runtime protection. And here's the bigger idea. Encryption is not just a checkbox. Key management matters. Who owns the keys? Who can rotate them? Who can access them? Are they managed by the customer or the provider? Those questions matter because encryption without good key management is like having a strong safe, but leaving the combination written on a sticky note. Now that we've covered data protection, let's talk about logical security controls inside the cloud network. This slide shows how we segment and protect cloud environments logically. In a cloud environment, we often use a virtual private cloud, or VPC, to create an isolated network space. Inside that space, we may separate systems into tiers, such as web, application, and database. Why separate them? Because each tier has a different exposure level and different security need. The web tier may face the internet. The application tier handles business logic. The database tier stores sensitive information. If an attacker compromises the web tier, we don't want them to freely move into the database tier. That's where segmentation comes in. VLANs, subnets, security groups, network access control lists, and microsegmentation help limit traffic between systems. Microsegmentation takes this even further by applying very specific rules to individual workloads. Instead of saying, this whole network can talk to that whole network, we say this specific service can talk to that specific database on this specific port. That's much closer to a zero-trust mindset. The slide also mentions WAF, or Web Application Firewall, protects web applications and API by inspecting application layer traffic. It helps detect attacks like cross-site scripting and SQL injection. But here's the exam trap. It protects web applications and API. It does not replace network firewalls, segmentation, or identity controls. On the outbound side, data loss prevention tools can inspect traffic for sensitive data like personally identifiable information or protected health information. So the big picture is layered defense. We use network isolation, workload level controls, application protections, and data protection together. Now let's move from cloud architecture into how secure applications are built and delivered. DevSecOps means we build security into the development process instead of bolting it on at the end. Why does that matter? Because finding a security flaw after an application is already in production is expensive, stressful, and risky. Finding it early is faster and cheaper. The first step is threat modeling. This means we ask, what could go wrong? During the design phase, we look at how data flows, who can access what, where trust boundaries exist, and what attackers might try. The second step is security testing. SAST means static application security testing. It looks at the source code or compiled code without running the application. DAST means dynamic application security testing. It tests the application while it is running. Think of SAST like proofreading the recipe before cooking. Think of DAST like tasting the food after it's prepared. Both are useful because they catch different problems. The third area is application virtualization and containers. Containers package an application with its dependencies so it can run consistently across environments. They usually have a smaller footprint than traditional virtual machines, which can reduce attack surface. For the exam, containers are generally considered more secure than full virtual machines because they are smaller and more focused. But in the real world, they still need strong configuration, image scanning, runtime protection, and access controls. The fourth area is API security. API are how systems talk to each other. REST API commonly use JSON over HTTP, while SOAP uses XML. Regardless of style, API needs strong authentication, authorization, rate limiting, input validation, and encrypted transport. Here's a good question to ask. If API are the front door for applications, are we treating them like front doors or like side doors nobody checks? That's the mindset DevSecOps brings. Security is part of the pipeline, not a final inspection. Now let's shift into evaluating cloud providers. When we use a cloud provider, we need evidence. Trust is good, but verified trust is better. This slide highlights common audit and compliance frameworks. SOC1 focuses on financial reporting controls. If the concern is financial systems and reporting integrity, SOC1 is relevant. SOC2 focuses on security, availability, processing integrity, confidentiality, and privacy. These are called trust services criteria. SOC2 Type 1 looks at controls at a point in time. SOC2 Type 2 looks at controls over a period of time. For security assurance, Type 2 usually gives stronger evidence because it shows operational effectiveness over time. ISO IEC 27001 is a standard for creating and managing an information security management system, often called an ISMS. In simple terms, it shows that an organization has a structured security management program. FIPS 142 focuses on validating cryptographic modules. If you care about whether cryptographic tools meet a specific standard, this becomes relevant. Common criteria, also known as ISO IEC 15408, evaluates AT security products using assurance levels. The slide also calls out portability and interoperability. Portability means we can move data and applications without being trapped by one provider. Interoperability means distinct systems can communicate and work together smoothly. Why does this matter? Because vendor lock-in can become a business risk. not just a technical inconvenience. If we cannot move, integrate, or exit cleanly, our negotiating power and resiliency go down. So when evaluating a cloud provider, don't only ask, is it secure? Ask, can they prove it? Can we audit it? Can we exit if needed? Can our systems work with it? That's how a risk leader thinks. Now let's look ahead at next-generation cloud capabilities. Slide 13, next-generation cloud capabilities. Cloud continues to evolve, and this slide highlights several technologies that are shaping the future. Edge computing moves processing and storage closer to where data is created. Instead of sending everything back to a central data center, some processing happens near the device: user, factory, hospital, store, or sensor. Why does that matter? Lower latency, less bandwidth usage, faster decisions. This is especially useful for IoT, healthcare devices, manufacturing, and real-time analytics. Artificial intelligence and machine learning are used defensively in security operations. They can help detect anomalies, identify suspicious behavior, and support faster investigation. But they also introduce new risks. If the data going into the model is bad, manipulated, or biased, the output can be wrong. Blockchain provides distributed, tamper-resistant ledgers. It can support data integrity and non-repudiation, meaning someone cannot easily deny that a transaction or event occurred. Homomorphic encryption is especially interesting. It allows data to be processed while still encrypted. In plain language, it lets someone perform work on sensitive data without seeing the actual data. That's powerful for privacy, but it can also be complex and resource-intensive. The key message is this: emerging technology creates opportunity, but it also creates new risk questions. What changes? What new dependency appears? What control must evolve? That's the security mindset we want. Now let's move into resiliency, because even secure systems must be able to survive disruption. Security is not only about preventing breaches, it's also about keeping the business running when something goes wrong. BCDR stands for Business Continuity and Disaster Recovery. Business continuity asks, how do we keep critical operations going? Disaster recovery asks, how do we restore systems after disruption? The foundation is the Business Impact Analysis, or BIA. This is the first step because it identifies critical systems and determines what the business can tolerate. Two key terms matter here: RPO and RTO. RPO means Recovery Point Objective. It answers, how much data can we afford to lose? If the RPO is 1 hour, then backups or replication must support no more than 1 hour of data loss. RTO means Recovery Time Objective. It answers, how long can the system be down? If the RTO is 30 minutes, the architecture must support recovery within that window. RPO drives backup and replication design. RTO drives failover design. The slide also mentions availability zones. These are isolated data centers within a region. By spreading workloads across zones, we reduce the chance that a single facility issue takes everything down. Data dispersion is another resiliency technique. It spreads data blocks across different storage nodes, so hardware failure does not result in data loss. Here's the practical point: resiliency must match business need. Not every system needs active architecture. Not every system needs near-zero data loss. But critical systems need architecture that aligns with business impact. So before designing the cloud solution, ask, what matters most, how fast must it recover, and how much loss can the business tolerate? Now let's bring everything together. Slide 15, Domain 1 Summary and Final Master Exam Tip. Let's step back and connect the full picture. First, we covered the foundation, the 5 essential characteristics of cloud, the 3 official service models, and the 4 deployment models. Second, we covered the actors: cloud consumer, provider, broker, auditor, and carrier. These roles matter because cloud security depends on clear responsibility across multiple parties. Third, we focused on the security imperative: shared responsibility, virtualization isolation, and encryption across data states. This is where the cloud security mindset really becomes clear. The provider may manage the infrastructure, but the customer still owns the data risk. Fourth, we covered governance: SOC audits, ISO standards, SLAs, portability, and interoperability. These are the tools we use to enforce expectations when we cannot physically inspect or control everything ourselves. And that brings us to the final master exam tip. Think like a risk manager, not just an engineer. In cloud security, you often cannot touch the hardware. You may not walk into the data center, you may not control the hypervisor, you may not personally verify every physical control. So what do you rely on? As you continue studying, keep connecting the technical concept back to business risk. That's how you move from knowing cloud terminology to truly understanding cloud security. If you enjoy this kind of content, don't forget to like and subscribe to our channel and check out our CCSP and CISSP playlist. See you in the next one.